So the last speaker of this workshop will be introduced by Gergely.
Yeah, more important. Well, it is really a pleasure for me to introduce Ernő as the last speaker of the conference, of the anniversary conference, and there are several reasons for that. And let me also start with kind of some anecdotal anchoring of Ernő into the unfolding and beautiful story of the 10 years of our conferences. And thinking back, the first conference, I think, was 2001, which, is that right? Which, 11, oh God. Anyway, but it certainly coincided with another event, which was a very pleasant trip to Italy, to where I was one of the external examiners of Ernő's PhD thesis, and I had the great honor to have the other experimenter being Sue Carey. And apart from that thesis being remarkably creative and is full of interesting new ideas, and it put on the screen basically the general area he has been exploring since then, whether babies have ways of representing multiple possibilities, multiple actions, and whether they have some sense of probability of multiple different events, and how that is maybe inherently related to infants' innate ability of somehow compositionally connect basic ideas or representations through logical operations. So it really relates to his current very strong and interest that goes together with Sue Carey's grand project and Agnes's work and about mental logic, whether there is before language any ability to make inferences like mutual exclusivity, like disjunctive syllogistic inferences, etc., negation, and these are wonderfully deep and interesting questions that are having a revival now. And this is so this is Ernő's continuity in this line. But one anecdotal thing I wanted to mention is that this was the time when Sue Carey had to come to the first VCCCD meeting very fast, very, very fast, in the car of Jacques Miller, in the new car of Jacques Miller, which was, I think, some red Lexus or something, and went with a 200 kilometers per hour speeds to Budapest. And that was the only time I saw Sue just for a moment kind of be seriously saying that I have to go for half an hour nap now before giving my talk or something. And the other short story I would like to say is comes. Are you set this up with this? there was a picture I wanted to show. If you could. So that was a little bit later when, and this is the story of how they got to Budapest to work here. I mean, Ernő and together with Agnes, they the most wonderful, maybe lucky event that happened during this 10 years for me is that I had a chance to recruit them as postdoctoral fellows, and that was around the time, 2005-ish, and you can see that I look just like now, but Ernő and the red-haired is Ági, so they have gone through great development since then. And the story is that I got involved. I was invited into an EU mobility, Marie Curie mobility grant that involved having postdocs. I could have 3 postdocs hired, but they couldn't be Hungarian. So because the idea was to move around in Europe for all of these young scientists. Now, it's a bit difficult to test Hungarian babies and Hungarian parents without speaking Hungarian, so that really was a problem, and the way that problem was eventually solved is just fiddling with the nationalities, as always, and going down to Seesaw, to Trieste, because I just realized that there are 2 wonderful PhD students there, of Jacques Miller and Luca Bonatti, and they are from Transylvania, which is a part of Hungary 100 years ago, and they speak better Hungarian than I do. So I made a plan, and I went down, traveled down to Trieste, and spoke to them, and I said that there is this possibility, and they can do whatever they want, whatever they are working on. The only thing is that I didn't tell them the title of the project, the Marie Curie grant, which was Disorganization of Embodied Self. And I knew if I mentioned the word embodied, then Agnes she's a serious woman. There's no way she would have moved to Budapest, so I kept that in secret. And she found out only later. But anyway, it all worked out very nice. And I'm sorry if it was a bit too long, but with this, I would like to ask Ernő to give the last talk of our wonderful anniversary conference.
Thank you, György, for this superb introduction. As you could see, György is always having these stories, but his stories sometimes go really far, far back to Ebbinghaus, and that's how we got all our scientific background by working with him. Over this last 10 years that we spent together, practically we really went over a large variety of topics. We studied agency attribution, contingency perception, how do kids understand violation of principles of naive physics, or even crazy things like cessation of agency. That someone would think that we really did esoterical issues, asking infants whether they have concept of death or this kind of thing. So we had a large variety of projects that were condemned to fail. But he was the person that supported all the risky projects that we did. And we worked a lot, we had lots of failures, but we used to say we even had some kind of logo that all this was contributing to our intellectual development at the end. Okay, it's now that I'm sitting here and seeing all these people and György here, I have a little bit of regret that I choose the topic that I'm presenting now. So today I'm going to speak about representation of possibilities, multiple possibilities if possible, and the role, if there's any, in early inferences. I could speak about other things, mostly social cognition stuff that we did with György, but boo, now the dice was thrown, so I can't really step back. I have to admit that I asked Gergely how to proceed, like what to talk about and how. And I remember there was a few people yesterday saying that even they asked Gergely how to present, and Gergely was suggesting them to go polemical, to present something that is debated and there are disagreements about. When I did my question, he was telling me to go straight. This is actually what I'm doing right now. I decided to start right away with the presentation of one experiment just to set up the context for the issues I'm going to talk about. Obviously, I didn't choose my experiment at random. I chose it because this was the very first time I entered into at least a conceptual replication of an experiment, mostly motivated by Luca in Trieste, who was showing me this paper first. I knew György's works on other domains, but I didn't realize he's interested in this topic. So the other reason that I chose this thing, because György is an author of this thing. This experiment was done here in Budapest with some nice Hungarian ethologists. And I have to admit, I have also a third reason that I choose to start with this experiment, and this is because I literally spent half an hour to put György's face on the experimenter, on this little puppet. So that's how he could become the experimenter in this project. So what is this experiment about? That's a comparative study that was designed to check the role of logic or disjunctive syllogism in this specific case in children's and dogs' search dynamic. So the way these kind of experiments work, they really follow a very simple protocol. It's called the invisible hiding procedure. There's an experimenter that is hiding a preferred object of the kids or the animals. This is very often like a rubber doll, a plastic dog, or just simply a ball. And in one of these three behind one of these three large occluders, and they just let the participants to search, and they measure searching time. Okay, these are the results. So as you could see on the right, I'm just going to pick up my pointer. So as you could see on the right part of the graph, that's where the children's performance is plotted. Do you see anything? So this part, kids become faster as they move to the third location after they found nothing in the first two locations. In contrast, this is not the case for dogs that seem to become very slow as they move to the third location after they found nothing in the first two locations. The authors proposed that in this specific case, the children's performance, at least, can be explained by applying logic. They suggested that kids eliminated disjuncts one by one via negating them as they work through a set of disjunctive syllogism applied consecutively. So if you do that, you have to come up with some kind of descriptions that the ball can be in location A or B or C. It's not in A or B, therefore it should be in C. So the idea is that whenever you eliminated sufficient location, you should get with certainty the location of the ball. I choose this experiment also because these kind of works are really nicely illustrating the kind of compromises that someone working on this field has to face. So this study, for instance, is a nice case of how we do experiments in cognition. So in this case, the logical operators that the authors wanted to test do not really reflect directly in the dependent variables. Moreover, it is just reflecting in the variation of uncertainty caused by the elimination process. This is usually in most of our experiments, but if you want to be sarcastic a little bit, for those that really go crazy for logic, we have to say that in this specific case, logic was tested through probabilities. Okay. The second point is that in in this kind of experience, there may be some hidden variables. For instance, the first slow decision-making, when people go to the very first location, they are the slowest. But these are also the moments when they have to really build a large variety of mental models to describe the scene. So in this specific case, there was only one object hidden, but imagine that there are 2 or 3 or more objects hidden. As soon as the amount of hidden object is increasing, the kind of combinations that you have to flesh out, that you have to generate is really growing, and when you have to update after something is eliminated, it may be really requiring a lot of effort. So it seems that these experiments have to deal with the balance of how many mental models are elaborated, how do you calculate the probabilities, and what's actually the logical background where you deal with these alternatives. Okay, there's also a third point that we have to emphasize, that in these cases, the performance crucially depends on some factors that are clearly non-logical and they may be task-specific. These factors are like, we need some kind of mechanism that is able to track and monitor the already eliminated alternatives. Because if we don't know what was eliminated, we will go random, we'll be certainly very redundant. In extreme case, we may go in infinite loops by just cycling between the already eliminated alternatives. Okay, the authors suggested that, in fact, dogs' performance can be characterized by something that is very weird nowadays to talk about. So something like, in terms of associations, associative extinction. So the idea is that how this invisible hiding protocol works, you have a ball that you put in a basket, you show that, look, there is a ball in this basket, the experimental visits all these occluders, and then at the end it shows that, oops, the basket is empty. So then the participants have to infer that the ball was left behind one of these occluders. Okay, the idea is that as soon as the dogs start searching and they start accumulating some failures with finding the ball, the response strength is declining. That's how they get very long search time. Okay, this is just another way of reformulating the problem. Let's get rid of associations. We may describe these problems in the following terms. Could it be that, in fact, dogs had some issues in determining these alternatives in terms of possibilities and be able to deal with multiple possibilities in parallel to solve this task? If they cannot do that, they can just go guessing. They have a bet, they go for one location, they find nothing, and, nothing follows. It could also be that they are very, very fine with determining these locations in terms of possibilities, but they lack other concepts, that of exhaustivity. For instance, they may not know that they have to check all the locations in order to guarantee success. So this could be that they suffer some kind of premature closure, and that's how they do not finish the search. Okay, right now we know that this kind of concepts, model concepts, notions of possibility are available in literally all the cultures that were studied. It's true that just the other day I found that there seemed to be a language in British Columbia where the indigenous people don't make a difference between what is possible and what is necessary. I didn't check yet the reference, but I did collect it. It seems that children start to use consistently models at around the year of 3. They use can, have, shall, could, must comes a little later. We have to observe, though, that all these cases refer to deontic models. That means that they seem to refer to rules, permissions, obligations, and the routes they take to get away from this. This may be that that's what we do with kids. They push them to get rules, and that's how they pick up the lexicon that is relevant for this case. So all cultures seem to have access to notions of possibility. Kids have access to it very early on, but we still don't know what does it mean for something to be possible. That's still a puzzle. Let's take the following example. This is like John that plans to transport his reptiles. He has some pet reptiles. He has to transport them from A to B, from mom to grandma for the summer. And he's a clever kid. He decided to put some holes on the box just not to suffocate his reptiles. And you could see that the holes are uneven. Some are small, some are big. Now, just by having an idea of what a hole means, that is just a physical delimitation of the space, so some entities could come out from this hole, we can drive a large variety of conclusions. So just knowing the size of the hole, we can infer the size of his reptiles. So if he's a clever kid, the holes are smaller than the reptiles would be. But he may be a clever kid, but maybe a bit fuzzy in making the holes. So maybe he had certain mistakes, because we could see that the lower hole is larger, there are some large holes up here. If this is the case, his reptiles may escape, but they may not escape all over. They could escape only through some relevant holes that have the right kind of properties. So if now John, instead of fixing the issue, is just vigilant, watching in which direction these animals are going to escape, he should spend more attention to the red area and little less attention to the blue area, simply because there are more possibilities up there and less possibilities down there. However, he may be a very clever kid, but not that clever. He would think that, okay, so now I want to do something with these alternatives, and I put a patch or something like an obstacle, but I'm putting only one, because I don't realize that I have to put these kind of things on all the relatively large holes. Obviously, if John is clever enough and it has access to a full-fledged system of inference with possibilities, he would put these obstacles on all the relevant locations, but not on the irrelevant locations. Okay, that's the idea. We can do a large variety, as adults, we can do a large variety of inferences with possibilities. We can take into account multiple possibilities in parallel. We can go even further. We are able to judge whether the conclusion of some inferences are possible, necessary, impossible, these kind of things. But we don't really know how challenging these issues are for the nonverbal mind. We know that representation of possibilities is really fundamental in all those cases when we have to deal with future-related issues. But we really don't know whether this competence is present in early development, potentially in pre-verbal years in the first year of life. So we don't know whether these kids need some kind of special experience to come up with this representation. We don't know whether language plays a role in this repertoire. And we don't know whether this is shared with other species. What we really know, and that's more or less certain, that in the absence of these abilities, infants would be locked into some kind of they would be locked in actualities, if you wish. They would not be able to perform even the simplest planning for problem solving. They would not be able to perform development of subplots in order to achieve a goal. That being said, so all those entities that lack disability would be forced to learn to pick up information through trial and error learning, and virtually we would see no real discoveries till these concepts are not in place. I was trying to come up with some theoretical points of how, but these are not really theories. These are just like the kind of scenarios that I could come up with. So it could be that kids at an early age have access to multiple possibilities, and they can use them appropriately. They can use them in the probabilistic inferences whenever they have to set up the premises of the disjunctive inferences and so on and so forth. It could be that this being available, we still cannot have any claims about whether the representation of possibilities comes in graded manner, whether they can be placed on a scale. We don't know whether they have access to approximate possibilities. Why not? We as adults, we can easily imagine, we can easily talk, discuss cases like, I had approximately 10 possibilities to get a job, stuff like that. The second case is something similar. So this would be like, infants may have access to multiple possibilities, but they cannot use them appropriately, in the sense that some other premises, while they do inferences with them, may be they cannot be integrated in the inferences. So it could be that despite being able to represent multiple possibilities in the same time, their decision making is not reflecting that. So in these cases, these protagonists would just bet on one alternative and find out what's going on. Very importantly, when they revise their bets in case of failure, they should be able to choose a next alternative, a next candidate from the list of possibilities that are valid, okay? Obviously, the last scenario is when you don't have access to representation of multiple possibilities. You may have access to one possibility simply because you don't really care to come up with a longer list of possibilities, and you stop your search whenever you identify the first candidate. And it could also be that there are no possibilities whatsoever, and all these alternatives are just physically defined. It's a little bit hard to come up with a good description of what does it mean, but if this exists, it's creating an interesting kind of situation where infants that lack representation of possibilities in general, they would live in some kind of epistemic illusion where they mess up the factive and non-factive evaluation of what comes next. This word would be a deterministic word, really locked to actualities. Okay, why do I say all this? This is because just not so long ago, a series of interesting papers came out that started to shape an interesting developmental story. These kind of questions are really not this new. There were people studying related issues earlier, but this is a really neat kind of experiment that has the style that I really like. So the experiment goes on the following way. Children and apes are presented with a very simple device that's an inverted tube, and a ball is released, and they get a super simple task to try to catch as many balls as they can. And this is it, that's the verbal aspect of the instruction. No other verbal competence is needed in order to fulfill this task. What we can see on this graph is that only 4-year-old kids are able to solve these requirements and put 2 hands in order to be certain to catch the ball, but not kids at earlier ages, even though we see a little bit of development over the trials and the experience these kids accumulated. And we can see that apes are really not having this competence. When this paper came out, we said, oh, yeah, but there were many other things that were not really controlled. So, in fact, it could be that younger kids have some issues in coordinating 2-hand actions. So, it could simply be that one object primes one hand if they would use 2 objects. That would prime 2 hands. And just when we thought about this, these people published the exactly same experiment as we wanted, showing that no, we are actually not right. So kids don't have a problem in using 2 hands simultaneously and coordinate them for this task. So when they had these 2 parallel pipes and they released 2 balls in each of them, so these are, I don't know, maybe we can describe them as mutually inclusive events. In this case, they had no problem whatsoever in putting 2 hands. And when they had 1 object released or 2 objects released, this really had no priming effect over what was going on. So it seems that it's a real phenomenon, and children at the year of 3, they are unable to take into account multiple possibilities in parallel. Okay, this is in stark contrast with what we did with Luca. So with Luca, we worked really several years, and we still keep working on infants' ability to represent possibilities, to develop probabilistic inferences. And one of our proposals was that if kids are able to do that, they have to go extensionally. Extensionally means that they have to be able to take into account in how many possible ways these events can unfold, and just compare the amount of possibilities, and that's it. One subset will win against another subset or partition. For really being sure that this is what's going on, and probability intuitions of infants are something functional, and they can use it for future-related predictions, we had to do the following experiment. I'm going to present one experiment, maybe 2, from this long series of experiments. We wanted to check whether kids anticipate a priori before they see the event, the more probable locations. And something that other people did almost all the time, to measure violations of expectation and looking time at the end of the event. So we had an a priori and an a posteriori thing. The experiment was run with 12 months olds. They were familiarized with this kind of scenes. Okay, you can see a ball bouncing in these rectangular frames. There are 4 holes, 4 exit points to the left, 4 exit points to the right. We took care of a large variety of things. For instance, that there was the sounds for bouncing in the wall. We wanted to convey some solidity, because at the very end, these are just yellow pixels on the screen. So we also wanted to be sure that in this specific case, the ball is bouncing on the vertical walls the same amount of time, just not to bias the left and right position. We wanted to be sure that there are 2 versus 2 exits, so the left and right directions are equiprobable. Moreover, in the test cases, oops, I'm sorry. It seems I'm going a little bit randomly with this. In the test cases, we had these versions, like 3 exits on one side, 1 exit on the other side. Again, we controlled the trajectory of the ball. You could see that the last trajectory is vertical. We can hear the sounds also during the occlusion. That should convey the idea that the motion didn't stop, and so on and so forth. We really invested a lot of time in designing this kind of experiment. So what we have is a scene where there is a ball bouncing in this rectangular object. That's how we set it up, this physical environment. This should behave as obstacles and direct the possible trajectories in left and right direction, depending on where the exits are. So at the first step, we wanted to measure kids' expectation. For this scene, when the frame became occluded, was just ideal, because then we got a homogeneous screen where there was no additional information, and we could simply measure what is the eye doing. You should see that we did not expect to see this more orthodox ballistic eye movement, when the eye moves from A to B in one shot. We just wanted to see whether the eye moves a little bit to the right or a little bit to the left, depending where the 3 exit side is located. And yes, at the end, we measured looking time, because that was like a good signature of surprise in a violation of expectation paradigm. We also ran a variety of controls. So this is something you have to do, because what if some perceptual after effect is driving the eye movement that looks anticipatory for us, is just a perceptual bias that kids would have. So we had some versions with frames that look perceptually similar to this one, but in fact, the holes on the that is corresponding to the multiple exit sides, now they were obstructed with some solid segments. And we had also this version where we really placed a proper barrier in order to prevent for the ball to exit from this side. So these were the versions that we ran, and these are the results. Up there, you will see the looking times. You could see that most of our predictions got fulfilled. In looking times, virtually all of our predictions. Kids look longer if the ball exited from the side with 1 exit, and also longer when the ball was passing through the solid wall, and this was the case also for the 3rd experiment. It's more interesting what was going on in the eye movements during the occlusion period. On the x-axis, you see the gaze coordinates in pixels on the screen. 0 is practically the middle of the occluder. And on the y-axis, you see the occlusion time. The time goes from down to up. As you could see that we had this kind of implicit preparedness for the more probable exit in the terminate version, where kids could think reason probabilistically, but we didn't have anything like that in the more deterministic version. At that time, we were a little bit surprised, and we even put these experiments aside for a while before publishing, and we allowed ourselves to think a little more. And then we come up with this idea, but okay, so in a deterministic case, when the trajectory of a motion is super well predictable, why to bother yourself to anticipate? Because at the very end, there is really nothing to learn. And we thought that it's a matter of information acquisition that drives anticipatory eye activities in the oculomotor activities in the probabilistic version. Okay, now some years after we ran this experiment, I don't know whether anticipating is really contributing to learning, but what is clear that if you anticipate, then you can correct your errors in much earlier, and you can come up with a more appropriate description of what's going on. Okay, just to recap, and from now on I'm going to focus only on the first experiment. So first, kids have to come up with an event representation. That is the ball, the frame, the exits. It has to understand somehow that these exits are relevant for the possible continuations of the scene. Then they should come up with some numerical grasp of what these exits are. There's 1 to the left, 3 to the right. And you should just understand that there is more to the right, so there is more possibility. That means more chance that the scene is going to continue in that direction. Okay, but there is one alternative. I remember that when we wrote up the first version of these things, we got an email from Tim Sharris, to whom Lucas sent this paper for, just to get feedbacks. And Tim was saying that, yeah, but what if kids do the following? They understand the event somehow, but instead of, after they come up with what is possible in this scene, they just have a bet. Okay, if they have a bet, at the end there are many kids, many trials, many bets, and overall there will be more bets that are targeting the site with more holes. That means that there will be more often those cases where kids form expectations in this direction. At the end, this would be converging to the kind of results that we are getting. They said, okay, but we have these experiments. These experiments are with lotteries. There are really lots of objects here, many blue, many yellow. If kids apply the same strategy, then we should see probabilistic expectations also in these scenes. But we should see probabilistic expectations also in these scenes when we are in the subitizing range. And our results showed that this is really not the case. So that's the trial structure that we had for the small set version, and we see that kids look longer for when they see improbable exit, but this was really not the case when they had to deal with large sets, with many balls. For us, this meant that, first of all, representation of possibilities for infants has to be discrete in some sense, and they don't have access to some kind of approximate description as adults can access easily. Okay, so that's what we have. On one hand, we have the findings from toddlers. So it is expected that these toddlers and preschool kids are very good in indexing the exit points of these pipes before the ball is released. They can capture the possibilities. They can capture the continuations of the scene in disjunctive manner, just simply describing these alternatives with propositional connectives, they say like exit 1 or exit 2. Alternatively, they can use a description in terms of possibilities. That's why this little diamond is supposed to mark. So they could just say, it is possible that the ball comes out from E1 but not from E2. It's also possible in conjunction with the previous statement that the ball comes out from E2 but not in E1. There may be other possibilities that are not true in this case, and some may be relevant actually. It may be relevant that it is not possible that the balls will exit from the two locations in the same time, simply because this is a case of mutually exclusive possibilities. And kids have to understand that there are many possibilities for interventions. They can intervene on the first exit, on the second exit, on both exits. But they also have to understand that the necessity condition that guarantees the success in this task is to put both hands under the arms of this device. On the right side, there are our experiments with 12 months old that is literally suggesting that the probability intuitions of these kids is based on the understanding of possibilities. So, okay, I got you to a new example of developmental continuity. I'm not going to solve it today, but what I'm trying to do is to come up with some fragments of the experimental projects that we are doing that is just trying to chart what's going on, come up with new ideas, get the limitations of the younger ones, the limitations of the older ones, and just get like maybe small steps toward an understanding of this picture. I'm trying to present 3 or 4 experiments. I'm not sure I'm going to have sufficient time for that. The first 2 experiments are just different versions of the search paradigm that I was presenting at the very beginning. One is a gaze contingent paradigm with infants. The other is a computerized version of that we ran actually with Luca. And yesterday he mentioned, why don't you talk about this experiment? So I invested some extra time to I needed to convert some old slides to put it. This experiment is not abandoned. Like every 3rd year, we think about a new version, but now it would be the time to have a closure. It would not be a premature closure. The 3rd experiment will be a case that we are doing with Neha Ketrapal. That is a variation of the inverted Y-tube experiment, but we are doing it on a touch screen. With some subsequent experiment, we are trying to check whether unequal possibilities can be understood by 5-year-olds. And the 3rd version is something that we do with Niccolò Cesanarlotti. It's the pupillometry of the possible. Let's hope that I'm going to have time to get to the end. Okay, so the first study. Gaze contingent experiments with infants. These are really cool things. When we present infants, people just give me like 2 more minutes usually. So that's how the experiment looks like. We have 3 cups on the screen that are occluded. My animated hand comes in with this coin, goes behind the occluder, and just like in the very first experiment I was presenting with the kids and the dogs with the invisible hiding paradigm. Now I show there's nothing in my hand, so you should infer that whatever I had in my hand remained somewhere hidden in or under these upside down cups. The paradigm was a gaze contingent paradigm. As I said, that means that kids were sitting in the front of an eye tracker. These are really cool things because that's the way to turn these little infants in some kind of supermans. You know, when I saw the first eye tracker, I thought that, oh, from now on, I don't have to do anything. I just potentially even control the experiments from home and kids will test themselves. It's not really true, and doesn't work that way. And moreover, it's not trivial how to set up and how to make working such a thing in technical terms. The trial looks like this.
See ya, Baba. See ya.
The kids are addressed. I believe in the lab, most experiments, even those that are not studying pedagogy-related issues, would use this kind of thing. So the hiding event is just in place. The kid's eye is directed to the center, and once this disappeared, they are allowed to fixate on these regions of interest, and if they have long enough fixations, then the cup will turn upside down. You could see that the kid was hesitating between these 2 cases before going to the last location, and finally he found the object. Okay, the search latencies are showing that as the kid is progressing from one location to the other, in fact, his search latency is increasing, so this performance is more similar to what dogs were showing in the 2001 experiment. However, we found something about disengagement. So kids were faster to disengage from locations that were checked later in the search process. For us, this meant that we should not stop with this paradigm and maybe give some other trials, because this may suggest that they have an idea that more search steps you have, it's more probable that you find something. Then we checked how are the steps developing during the experiment. These are ABC locations corresponding to the locations of the cups. So kids supposed to go for location A, check it, and if there is nothing, they're supposed to move to location B and check it. If there is nothing, they're supposed to move to location C. However, this would be the efficient search that appears only 33% of the cases that we have in our trial. That's very little. 66% of the cases, they have redundant searches, meaning that they cycle between the first and second check location before going on. This is something that we see in the animal literature very often. Then we thought that, okay, let's do a little bit of training, and let's get gradual to the 3-location test phase. So before getting there, we decided to have a 2-location version. That's the result from the version with, maybe I had, yes.
See ya, Baba.
No, sorry, so this is a different thing. The results. So you could see that when they get from step 2 to step 3, they are reaching a plateau. They get significantly faster than they had in the very first experiment, but we still don't see the kind of dynamic of the surge that was present in children. Then we said, okay, let's do a visible hiding, because if we do a visible hiding, then there will be cases when they are not going straight to the location where they saw the coin just being hidden. So there may be cases when they go the other way. So if they do that, then they should have a lot of experience of what does it mean to do elimination of alternative via disjunctive syllogism. Okay, so that was the familiarization. We had 8 trials like that and only 4 test trials. And guess what? In experiment 3, the pattern was exactly like in experiment 2. However, I have to add that contrary to my expectations, there were only 58% of correct trials in the familiarization. That means that contrary to what we expected, kids didn't really care of this coin. So they were not interested in what we thought they're supposed to be interested. And this is telling a lot about how this kind of infant experiment works from a methodological point of view. The second study on the same topic, it's something that we did, we are doing, we continue to do with Luca. That is tapping on an interesting issue with older children. So in this case, we tested 6-year-olds, and we wanted to find out an intriguing case after we replicated, at least conceptually, the results of the very first experiment. So this was just, we were presenting these 3 locations on the screen and telling to the participant that there is one apple hidden in one of those locations. And whenever they press a button on this button box, the corresponding, the content of the corresponding location will be unfolded, and they will see whether they managed to catch something or not. And again, we measured search latencies. As you could see, initially they are slow, and then they get faster as they progress. In these graphs, usually we only depict those trials where they find the apple at the very end. These experiments are very carefully designed in the sense that they have equal probability to find the ball in the first, second, and third choices. These are not mapped to actual locations. There is always a little decision tree in these programs that are managing to do the right kind of job. What we wanted to ask whether the following issue matters. So in all these cases, the choice alternatives and the alternative possibilities overlap. We have the same amount of choice possibilities, like in this case, like motor actions, than possibilities we do. We were thinking that this is something that we can dissociate and check which one plays a role, which one is actually defining the search time. So we designed this experiment where the protocol is exactly as before, with one exception. We put a little bug, a small spider on this. We said that, okay, you have to avoid the spider, but whenever you had the first choice, you can go on. You can have access to the initially forbidden location. The steps were like this, and the predictions were this. So if the choice alternatives are those that define the search time, we should see equal search latencies in these 2 steps, in these 2 consecutive steps. If the probability of success is the one that is defining the search time, then initially they should be slower, then faster, and even faster. Okay, and you could guess that this is exactly what we got. So this search latency pattern looks exactly like this. There is no difference whatsoever. And then we just checked if we have just one location what's going on. We thought that in this case, you should not take into account anything about possibilities because you are constrained to do one thing. So this is the deterministic case. And then we see a plateau with the search time. Okay, and now I shift very fast to the second kind of study that I wanted to present. This is a modified version of the inverted Y-tube task that we saw before. We do it with Neha Ketrapal. She should be somewhere in the audience, but we do it on a touch screen. Initially, kids are familiarized with these pipes that are just single vertical pipes, and we teach them how the system works. To our surprise, they're not super good with touch screens, despite they have a lot of access to iPads and those kind of things. And in the test case, we had the following version. It's just an inverted Y-tube. We categorized the answers as correct, incorrect, and misplacement. It was correct whenever it was incorrect whenever the participants targeted just one exit. It was correct whenever they targeted two exits. Misplacement when they did not target the pipe. And so obviously, in these cases, you didn't have too many alternatives, so you either put it on one pipe, and then you didn't catch it in approximately half of the cases, or you put it in more in the middle, and you managed to catch the ball in all the cases. But you have to observe that if you do this, this implementation, then the chance level is very small. So if you go random, it's very hard, I mean, to put it the right way. And these are the results. Our results are a little worse than Suddendorf's results are. However, we see the same developmental pattern. Older kids seem to perform rather well. The 3-year-olds seem to perform worse than the 4-year-olds. However, they are all of them beyond chance. So they all managed to express some understanding of this task. And now the main manipulation that we did was the following. So we changed this tube dramatically, and we implemented 2 bifurcations. With this solution, we managed to come up with possibilities that are unequal. In most of the traditional experiments, people deal with equal possibilities. So in this case, this has a higher probability than the other two, 50%, 25. So if kids want to optimize their chance to collect as many balls as possible, they should go for B and C. But this is really not what we see. They are completely at random. They go for combined exits only about 30% of the time. So it seems that whenever the possibilities are unequal, they are just collapsing. Study number 3, it's something that we did with Nicolò. With Nicolò, we thought that, okay, all these experiments are studying the access to kids' ability to capture something in terms of possibilities indirectly. So our experiments did it through probabilities. Suddendorf's experiments did it through some kind of complicated foraging strategies. Why not to go straight? Straight meaning that to show some scene that is ambiguous and check what's going on with, in line with some other dependent variables. And our dependent variable was pupil dilation. We know from the classical literature that whenever we load the working memory, pupil is dilating in a more or less linear manner. Our experiment was, I jump over just this thing because it seems that I'm running out of time. Our design was the following. We had 10 and 14 months olds among our participants. This was 2 groups of kids, and they saw the following scenes. There are 3 objects presented. In this specific case, 2 to the left and 1 to the right. You should note that all of them have one shared fragment, so the upper part is red. At a certain moment, one of these, these lateral objects are hidden by these vertical bars, and an object would appear from left or from the right, just like here. The idea was that if kids have access to possibilities and they can represent what's going on, then they should realize that there are 2 possibilities in the scene to the left and 1 possibility in the scene to the right. And now I'm showing these videos. So this is what Nico did, very nice animations that I like. They are associated to some sounds that we don't have right now. So this was just to show them that they have a shared fragment, and this is a test trial. So guess what it is? Okay, and this is our data. Up there, they are the 14-month-olds. Here, they are 10-month-olds, and that's the time since the objects, since the fragment's appearance in the center. We could see there is nothing much going on in the pupil dilation with the 10-month-olds, but we see a very nice effect in favor of the 2 possibility condition in the 14-month-olds. If you want to stop here, we could conclude that kids do have this early competence to keep in mind 2 alternative possibilities in parallel. However, this may not be the case. A very simple model, it's a tentative model to depict what's going on is that, so you see the ambiguous object, not the object is ambiguous, but the fragment that you see that is not allowing you to immediately re-identify the identity of the object. And if you care what's going on, then the only thing is to come up with some hypothesis. And if you have multiple hypotheses, then you represent this in terms of possibilities. This will load your working memory, and then you end up with pupil dilation. However, it could be that whenever you see the fragment, you are not going through a hypothesis, but you try to simply recall what the objects were at the source location. And that could also contribute to the pupil dilation. And it also could be that whenever there are more than one alternatives, you say, oops, I don't know what's going on. So you are ignorant. And ignorance may cause pupil dilation simply because of the immediate uncertainty that it's causing. Before or instead having final conclusions, because I ran a little bit out of time, these are just some pictures. It's super cool that the texture and the color is similar. This is from the Piagetian era, where Piaget and his followers, collaborators, tested kids at a variety of ages with every kind of instruments, like marbles placed in different jars, roulettes, and at the end they concluded that these abilities that we are talking about, the probability intuition, the disjunctive abilities, other more sophisticated things when reasoning appears after the year of 12, when they get to the formal period of reasoning. However, on the left, we see a picture that is from Pompeii, Italy. There are two guys playing dice. So the idea is that just well before the first attempt to formalize our probabilistic intuitions in the Bayesian formula, and even earlier in the time of Laplace, people did get involved in probability-related game, and they were able to judge the amount of risk that they take when they bet on one or another alternative. That means that they could rely on some abilities to deal with these probabilities in extensional way, like to flesh out the possible combination and just count how many of these alternatives are in favor of one or another bet. And we assume our kids are doing something very similar on a small scale. Thank you very much.
Questions?
Hi, thanks, Ernő. Can you show me the picture of the box with that they're going to keep the reptiles in, move the reptiles in? With the one where you have the Band-Aids over the bandages? Or?
I don't have any copyright on that, you should know. I just copied it from the internet.
So when part of your argument was that, like, if you want to cover all these holes, you got to recognize that there's multiple possibilities. You got to be representing multiple possibilities, right? If you want to solve the problem. But I don't see why you couldn't just solve this problem by, like, looking at a hole and simulating your reptile coming out through that hole, projecting into the future. So that's
okay. So you can project it in the future, but all those simulations would work only if you get feedback about whether your simulation was right or wrong.
Well, hold on.
Okay.
So I can run one simulation, right? And I simulate my reptile coming out that hole, so I cover it up. And then I look around at the box again. And I find another hole, right? And I check, can I simulate it coming out here? And I do. And so I cover that hole. So I can solve this problem this way by running sequential simulations without representing any of these as possible, as merely possible along the way, right? I just need to check whether I might assume that it's actual and prevent that and stop that without representing it as a possibility, and certainly not representing multiple possibilities at the same time.
Yeah, you can do that. The way you are talking about possibilities in this context, it really hinges on what do you mean by possibilities. If possibilities are just contents that are not true in the present, but they have the propensity to be true, then what I'm talking about is not different from what you are talking about. It is just a matter how we identify possibilities. And once possibilities are identified, we can go in many different ways. So that's how the origin of this identification is very relevant. I have to say it's very unfortunate that practically none of our experiment allows us to do that, except maybe the experiment we do with Nico, if we get the right kind of control at the very end.
Okay, any other question?
Thanks for a very interesting talk. How do you reconcile your your contrasting findings with the 1 versus 3 option with the bouncing ball, and then the bifurcating tube? Could you say a little bit more about how you make sense of those contrasting findings?
The one problem with our experiments, the infant experiments I'm talking about, we were more or less aware of these issues when we did the project, is that we can get very similar results in our case, even if our participants do not really compare multiple possibilities as we used to think. So then the question is whether it's really a discontinuity with the infant data and the inverted tube data. Because if the case is that our infants, in fact, were not doing the kind of computations that we expected them to do, then there is no continuity. So then we just have to find out the right developmental path, and I assume also Luca has some ideas in that direction. But what I would like to add is that if this would be the heuristic that infants in our experiments would be using, then this heuristic is available in all the other probability experiments. So now we are calling it the billiard experiment, the one that is dealing with the spatially defined possibilities as exits. So if we focus more a little bit on the experiments where we deal with object identities and we have multiple objects bouncing in these jars, these are all video animations, so we had to be a little bit careful of how to implement these things. So you could apply the very same heuristic if you have lots of objects, okay? Nothing prevents you to say, okay, this one is going to exit, okay? You could do that. So if you apply the same heuristic, then the data should reflect this heuristic. However, this is not the case. You know, someone may say that the experiments with large lotteries, with large sample lotteries, are more complicated and more complex visually, it's more demanding to find out what's going on. I have to say that this is not truly the case, because among these many experiments, we had versions where the object that was exiting was far from the exit. So you can imagine that down here there are blue objects, 12 of them. Up there are 4 objects, let's suppose yellow. And everything is occluded. And now we see that the one appears down there is the one that was far. Okay, so this is surprising for infants at 12 months of age. And it's surprising because they found problematic to understand how comes that this object managed to travel through this very dense and very packed amount of other kind of objects. So the picture is not super clear, but we have some hints that our initial intuitions were more or less correct. It could be that kids can represent multiple possibilities, but they don't rely on them exhaustively. So even in those cases, we should get related results. For instance, if kids could capture only 2 possibilities out of 3, but still 1 from the other side, that's still sufficient to have the expectation that we were talking about. There are several scenarios that are available. But in this case, we would need to claim that what is developing is something, what comes into the picture is some kind of operator for exhaustification, or something like that. And there may be people here in the audience working directly on these issues in the language domain with these junctions, the free choice problem and others.
You briefly mentioned modal language, and it's true that even 18-month-olds use modal language. But the fact that they use it doesn't mean that they understand it in an adult way. And I guess the question is, do you know any evidence that 2-year-olds and 3-year-olds understand the modal, even in the deontic context correctly?
No, I don't.
Okay. Yeah. Because I would be very interested in that.
There may be 7 or 8 papers dealing with this issue in total. So,
but are there 7 or 8 that suggest they do?
No, these are corpus analysis in most of the cases.
Our attempts to find spectacular in this analysis up until age 7.
I don't want to have any commitment there. We didn't check those because in Hungarian this is very hard. It comes in a very complex syntactic and morphological forms.
In all languages. I mean, the fact that they don't understand it doesn't mean they don't have the concepts. It may just be the language acquisition problem is very hard.
It could be. It could be. But I really prefer to have no commitment in that direction.
If you're looking for the concepts, and if they understand the adults, if they understand that language in the adult way, then you're done, right? But I don't think that's the statement.
No, it's more complicated than that.
Last question.
Hey, Ernő.
Just
So I want to bring up a topic that was discussed a couple times yesterday, and that's the issue about implicit versus explicit. And you know, the language understanding question also touches on this. Certainly Piaget thought he was talking about explicit reasoning at age 12. And when we think about 10-month-olds, for many people, the thought comes up whether or not this is an explicit theory or representation or knowledge versus just something implicit. So I'm wondering what you think about that distinction, and just to nudge you in a particular direction, I'll share with you some new data that we have, which is if we put 2.5-year-olds in the DAX situation with a ball and a DAX and say which one's a DAX, and we don't tell them we want you to point at who wins, then their eyeballs don't go via disjunctive syllogism. If we just tell them we want you to point at who wins, now their eyeballs go via disjunctive syllogism.
Am I allowed to show a slide?
Yes.
Honestly, I prepared 3 versions for this talk, a short one, a medium long one, and a very long one. And I chose the short one, and it became too long. This means that we tend to underestimate our abilities to present some data. In fact, we did run experiments on disjunctive syllogism and this kind of elimination of alternative while checking eye movements, inspired exactly by your work. This experiment looked like the following.
Akarsz velem játszani?
So you could hear at a certain moment someone asking, would you like to play with me? And then some music comes. So if you listen to this music is not informative about which person is doing the music. But if you have speech, and now you will hear that, would you like to play with me, and some other things. So in this moment, kids may set up the alternatives, like the left one is speaking or the right one is speaking. By the way, these are not twins, they were just a colleague of ours, we edited them this way.
Akarsz velem játszani?
The eye is directed to
Szia,
the center.
baba. Nagyon örvendek, hogy jöttél. Csináljunk közösen
Okay,
valamit.
which one is speaking? Okay. Many data. So up there is the music, down there is the speech. The prediction was that in the case where the eye starts from the occluded, semi-occluded phase, it should go to the other side, learn that this one is not speaking, and move back. When there is music, and the eye starts from the semi-occluded phase, it should go wherever, we don't know. And if we merge the two graphs, we see something like this. I believe the upper one is the one with speech sounds, the lower one is the one with music, and we see that in this specific case, kids starting from the semi-occluded phase and hearing the speech sounds and wanting to find out who is the speaker, they move to the other side and back. And if they hear music, they are not doing that. We have not very strong, but still a relevant difference at the tail of this, at the end of this 3.5 seconds that we measured. It's completely implicit. It does look similar to what you did, but it's not what you did, because if we check the distribution of the different kind of gauge shifts, they could have 1 shift, 2 shifts, 3 shifts, 4 shifts, 5 shifts. We see nothing, because this is a free task, so we don't have a termination of the trial if they solved it. So they just look back and forth. If we check whether we have more or less this double check cases in this experiment, we see that no, they don't. So in the music and in the speech sound cases, we have the same amount of eye movements. So it's trickier in some sense, but we do have some sign of doing it implicitly. How old are the kids? 10, 12.
Okay. Thank you, Ernő.
Well, I have the very pleasant and pleasing task to be able to close that conference. Now, it's a very funny feeling, because I feel like I'm closing a very successful and rich and to many of us very personally satisfying and fulfilling conference, while I'm realizing that the conference is just starting. So time is a very subjective thing, and I did think that this was an excellent closing conference, much better than I have anticipated, though I anticipated a good one. And I am very glad that, and I hope that there are some people who share this intuition. I would like to thank for all of you to have come. I would like to thank George Soros to make all this possible, and in spite of the way he's being treated by this petty country here that is throwing us out. But I am pretty sure that as the conference and its strength represents this, I think there is enough potential apart from the objective financial potential that his foundation has provided us. There is a living and strong university that will survive this rather taxing exercise of moving to another culture in another city, and I am sure and motivated that we will show that the university will thrive, and it will be available to the Eastern European students. As it happens, Vienna is 2.5 hours from Budapest. Used to be called Austro-Hungarian monarchy. But anyway, the future for the continuation of that level of scientific work is objectively possible, and we will do all that we can to do that. So once again, thanks for everyone to have come and participated, and thanks for all of those kind of leading figures that we have invited in the first year of the 10 years ago to the conference, and who have now sent their representative new generation, wonderful people who all have come, and the kind of mature guard, I would say, have also come and are with us to celebrate this 10th anniversary. Thank you very much.